Hello everyone, this is Mr. V. Hill, and today we're going to be talking about solving quadratic equations. And we're going to be solving quadratic equations by two different methods today. The first method we're going to be talking about is by graphing. And we'll just start out with a quick example here. And so the equation we're looking at is 3x squared equals 12. So basically we want to figure out what values of x will make this statement true. And hopefully we can just look at this a little bit and we'll notice right quick that obviously if x is 2, we're going to get a true statement out. Because 2 squared would be 4, 4 times 3, 12. So that's one value that will work. There's also a second value that we might be able to see really quick, that negative 2 will also work. If we plug in negative 2 for x, then the square of negative 2 will also be a positive 4. 4 times 3 is 12. So we know what the solutions are going to be, but we want to go about this in a manner which will work for equations that aren't quite so obvious. So the basic idea is that a quadratic equation in what's called standard form is going to look like this. A times x squared plus b times x plus c equals 0. Okay, where a, b, and c are just numbers, and we have to have 0 on one side of the equation. The whole point of this is that if we have the equation in this form, what we're going to do is we're going to graph the function y equals ax squared plus bx plus c, and then we just look for the y-intercepts. Because the x-intercepts are going to occur when the y is 0. So we know what values of x, when we plug them in, will give you a y of 0, like we have up here. Right? That's the basic idea. So with this equation, 3x squared equals 12, notice that we don't have 0 on one side of the equation. But that's an easy thing to fix. 3x squared minus equals 12. All we have to do is subtract 12 from both sides. And all of a sudden we have 3x squared minus 12 equals 0. So what we're going to do is we're going to graph y is equal to 3x squared minus 12. Okay. And then just look for where it crosses this x-axis. This is a pretty easy one to graph. Notice that there's no bx term in here. So we know that the line of symmetry is going to be the y-axis. We can get the vertex or the y-intercept as well just by looking at c here, subtracting 12. So our y-intercept will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right here. And that's also going to be the vertex because it is on the line of symmetry. And then we can plot a couple more points, or we just follow the whole slope idea. Normal parabola, we go to the right 1, up 1, to the right 2, up 4. But since a is 3 here, we're going to go up 3 times that much. So to the right 1, up 1, 2, 3. We'll have a symmetric point on the other side. To the right 2. Then instead of up 4, we're going to go up 3 times that much. So 4 times 3 would be 12. Oh, what do you know? That takes us right up here on both sides up to the x-axis. Oops, I'm sorry. Not there. At negative 2, 0. Notice here, x is negative 2, x is 2. Those were the values that we figured we'd have right from the beginning. So we just sketch in our parabola. And just by graphing, we can quickly see that the x-intercepts here occur when x is equal to 2 and when x is negative 2. Those are our solutions. And of course we can check those by just plugging them in. So if x equals 0, or excuse me, x equals 2, we plug that in. 3 times 2 squared. We ask ourselves, does that actually equal 12? Yeah, it sure does. Plug in when x equals negative 2. And we ask ourselves, does that actually equal 12? Yes, it does. No problem. Now, of course, notice here that our x-intercepts were nice integer valued coordinates. That is almost never, ever, ever going to happen. So, when we're solving by graphing, we're pretty much only going to ever get approximate solutions, even with the calculator, because the calculator will not give you irrational solutions or even decently expressed rational solutions most of the time. So, we need a different way of doing this. So, graphing, it's only going to give you an approximate solution. Let's try something else. The other method that we're going to cover today is called opposite operations, which is the basic thing that we've been doing all year with solving equations, undoing what's being done to x. For a quadratic equation, so this only works if b equals 0, meaning the line of symmetry is the y-axis, and that's that, which of course is rarely the case. If b isn't equal to 0, then there's some other tricks that we can do, which we'll get into later. But let's just work through the same example again. Again, 3x squared equals 12. And all we're going to do is we're going to undo what's being done to x in reverse order of operations. Of course, between an exponent and multiplication, reverse order says we need to undo this multiplication first. So we undo multiplying by 3 by dividing both sides by 3. Of course, that's going to cancel that 3 right there. So we're left with x squared is equal to 12 divided by 3 is 4. Then we need to undo squaring. And if you recall from a couple videos ago, the way to undo squaring is to take the square root of both sides. But not just the square root, we need to take the positive and the negative versions of the square root. And when we do that, now then the plus or minus square root will cancel with this squaring. And therefore we are then left with simply an x on the left-hand side, and then the positive and the negative square root of 4 on the right-hand side. But of course we know what the square root of 4 is. 2. And of course this plus or minus means that we actually have two equations. We have either that x is equal to this positive 2 or x is equal to the negative version of 2, which is exactly what we found last time. And we checked both of these solutions. So that's the basic idea here. So of course we'd say our solution set consists of the set of both 2 and negative 2. And that's going to be the case most of the time with quadratic equations, that you'll end up with two solutions. They're not always going to be symmetric about 0, and sometimes you'll have basically a repeated solution where you only get one, but we'll deal with that in a little bit. Okay? Let's work through another example just to show you some weird stuff that can happen. Let's say 10 is equal to 2 times x squared plus 60. Okay, now when we're solving using opposite operations, we don't need the equation to be equal to 0 on one side right yet. That's only for solving by graphing. It will be true when we get to quadratic formula as well. But for right now, notice the x just appears in one spot. So immediately we can undo what's being done to x. But we want to undo in reverse order. Of course, first thing happening to x is squaring. Second thing happening to x is multiplying by 2. Third thing happening is adding 60. So we're going to undo those in reverse order. So first thing, let's subtract 60 from both sides. So that's going to leave us with negative 50 on the left. Of course, these cancel. And we're left with 2 times x squared on the right. Stick with black here. Next, we undo this multiplying by 2 by dividing both sides by 2. So that those will cancel. Negative 50 divided by 2 is going to be negative 25. So we have negative 25 is equal to x squared. So we're going to undo this squaring by applying plus or minus the square root to both sides here, because that is how we're going to undo the squaring. And so we're left with plus or minus the square root of negative 25 is equal to x. So now all we got to do is figure out what the square root of negative 25 is. Whoops. Yep, we can't take the square root of a negative number. Not in Algebra 1 right now. Later on you will be able to, but that's the basic idea here is the solutions involve this square root of a negative, which means there are solutions, but they're just not real numbers. So we say no real solutions. If you want, we can check this by graphing. So if we were to check this by graphing, what we need is we do need 0 on one side. So we subtract 10 from both sides and we just have 0 is equal to 2x squared plus 50. And well, heck, without even graphing it, we can see here the y-intercept is 50, way above the x-axis, and it's opening up. So if we were to graph y equals 2x squared plus 50, it's opening up and the vertex is way above the x-axis. I mean, that's going to be somewhere way up here, and it's never going to touch the x-axis. So solving this equation is really equivalent to finding the y-intercepts of y is equal to 2x squared plus 50. There aren't any y-intercepts, so there's no real solutions. Let's try one more example here. Let's do example 3. Maybe x squared plus 12 is equal to 4x squared minus 12. I have a funky looking 2 there, but that's okay. You get the idea. So notice our x is appearing in two different spots. So first we definitely have to combine the like terms first. Notice there's also no just x term. These are both x squareds. That's great. Which really means there's no b times x term in there, so we can solve this with opposite operations. But first, of course, we have to combine the like terms. So if we subtract x squared from both sides, that'll get rid of that, and we're left with 12 is equal to 3x squared minus 12. And now we only see the x in this one spot. We can undo what's being done to it. So the first thing being done to x here is the squaring, then multiplying by 3, and then subtracting 12. We just undo those things in reverse order. So first we undo the subtracting 12 by adding 12 to both sides. That makes those go away. 12 plus 12 is, of course, 24. Now we can divide both sides by 3 to get rid of that. 24 divided by 3 is, of course, 8. And then we're going to take plus or minus the square root of both sides in order to undo the squaring. And now we have that plus or minus the square root of 8 is equal to x. So there's our two different solutions, the positive square root of 8 and the negative square root of 8. Now one quick thing here, we do want to write our solutions in simplified radical form. 8 has a perfect square factor of 4. We pull that perfect square factor of 4 out, take the square root of it. This is going to be plus or minus 2 times the square root of 2. You need to go back and review a little bit about simplified radical form. Now, if we want to check this with a calculator, all we have to do is really plug those values in to our original equation. So let's take this, the positive version. Sorry about that. So first, well, we're going to need to plug that in. So x squared plus 12 equals 4x squared minus 12. Let's see what the left-hand side gives us. We're going to take 2 times the square root of 2. Square that, plus 12. That gives us 20. The right-hand side, when we plug that in, 4 times 2 square root of 2 squared minus 12, also 20. Fantastic. We can try this with the negative square root of 2 as well. Negative 2 times the square root of 2 squared plus 12. That's the left-hand side with the negative 2 root 2 plugged in. That also gives us 20. And then the right-hand side, 4 times the negative 2 square root of 2 squared minus 12, also 20. So both of those solutions work. And that's the basics of solving by graphing and opposite operations. As remember, solving by graphing will usually only give you an approximate solution, and doing this with opposite operations is only going to work when b is equal to 0. We'll get into some other techniques to solve when b doesn't equal 0 next class. All right, that's that.